Hi, good evening. We are using this recording to discuss Unit 6 of CS2 data structures and algorithms. And this topic is on trees, not the one that you can find outside, but this is a tree data structures. And when you look at trees, it is different from what we have been discussing all along. Before that, we are only dealing with linear data structures. In the next slide, you will see what I'm trying to say. And from now on, we are going to look at non-linear data structures. Okay, so let's begin. Right, so we recall that in linked list, we have the data stored inside one list node. And linked list is a class by itself. And when you create the linked list, you are just having a pointer, the head pointer. Right, the head pointer will actually point to the first node, and then the rest of the list or the rest of the vertices or nodes contain the next value. So from the head, you can traverse one by one using the pointer that linking these vertices together. Okay, from the first node all the way to the last node, and there's only one pointer, and we say that this is linear. Of course, before that, we also learned array. Array is also considered a linear data structures because you can use one index and then you can go to the next location by increasing the index by one. Of course, we say that linear array is actually dynamic access. Okay, you can actually use the index to go to somewhere in the middle. But for a linked list, you want to go to the middle, you must traverse a list from the beginning until the place where you can find the elements. So these are linked lists, linear data structures. And we also mentioned that with this either array or linked list, we can treat this as the basic building block. And by using this, we can create other ADT. Right? For example, we discussed two ADT created using linked list or uh, uh, array, right? For example, a stack. We say that a stack is a collection of data that is accessed in the last in, first out manner, LIFO. Yeah, so the idea is a stack basically is an ADT of three operation, the three basic operation. Of course, there are other method inside there that allow us to do other thing. But basically, you have something called the push and the pop, the main two operation. And we know that you can use array or linked list to implement this stack. So for the push, you can imagine using a linear linked list where you add to the front. So you add front to the list, and when you pop, you just remove front, right? So we can use existing or the what we have created currently or already created. We can use that to implement other data structures. Right, so we know that push is to push one element on top. So in this case, if it is linked list, we just add to the front of the list. And then pop is to remove it. So remove front. So if you are using the array to do it, you just have a pointer pointing to the last element in the array. When you pop or push, you just push one element and move the index to the next index. When you pop, you just move the index back, and then assuming that the value is already removed. Of course, inside here, we can also have another method called pip to look at the first element. So recall that we say if this is an ADT and this ADT allow us to use only three operation. If you try to do other things, like for example, go to the middle of the list, it is violating the ADT. Yeah, so we cannot do that. Okay, so we can use that to help us to do a lot of things to actually simplify or to uh, make the operation, the algorithm more efficient. We will give you an example in maybe some tutorial question. And then of course, similarly, we can use queue. We can do a queue, right? So again, queue can have three operation, the basic three operation. And again, we can use linked list or array to do it. And because queue have these two end, okay, you add to the back and then you remove from the front. So therefore, if you use just the linear or basic linked list with only add front and remove front, you will not be able to implement a queue. So therefore, we have this variation of a tail linked list. right? So you created a linked list and then have one additional pointer pointing to the back beside the front pointer. So to add, you just use a tail pointer to add elements. To remove, you just use a head pointer to remove elements. So this is what we call a linear list, linear data structures. So now we want to look at non-linear data structures. The word seems to give us some impression that it's going to be more difficult, but actually the concept is the same. Right, so this is Q, so NQ to the back, DQ from the front, okay? And then of course we can pick to look at the first element, get front, yeah? Right, so tree, this is tree in nature, right? So you have the root below the ground, and then you have branches, and then you have the leaf. Yeah, so this is something that we see all every day outside when we are moving, leaving our house, we will see some trees. Yeah, so the concept similar to this, but not exactly. Okay, because computer science is a little bit from different from real life. So a tree in computer science looks something like this. The root is actually on top, okay, whereas the normal tree, the root is actually below. Anyway, we will look at some definition and so that we can use this definition to help us to discuss. So a tree, it is non-linear because every node could have more than one pointer pointing to other vertices or other nodes, and that's why this is non-linear. Okay, so we have a node, and then we have another. So what this is actually giving us a subtree, right? So in this case, you can look at a tree, and then you have the subtree. And one thing that we notice straight away is that the tree can be recursive. Yeah, yeah. So we look at some definition. First of all, the vertex. Okay, data object in the circle in the tree are called nodes, or sometimes you can call it vertices, especially during the next two or three lecture later. We are going to look at graph. So in graph, we call them vertices because it's actually a vertex representing some location and so on because it's a graph. Yeah, and then the link between nodes are called edges. Okay, so we have nodes or sometimes vertices, and then we have the edges connecting the vertices. Yeah, so again, to say that this is non-linear because one node or one vertex can connect to multiple vertices, not just one. Right, and we can also talk about some relationship between vertices. Right, so first of all, we say that A, in this case, A here is actually the parents of B and C. Right, so previously we say the neighbor, right, because it's only one node, one neighbor. But now A point to two children. Okay, so B and C are children of A, and A is actually the parent. So of course, then you have children, right? Yeah, so B and C are children of A. And then we say that B and C are sibling because they have the same parents. So this all these definition will be used later on when we are, for example, discussing heap or priority queue, right? So we will talk about the two children, and then the left child and the right child. We will look at them later on. Okay, and then of course, parents can be also described as ancestor because parent is just one level. Ancestor could be multiple level. So we say that D, in this case, is actually the ancestor of B, right? So in our normal term, we say that D is actually the grandfather of B, but it could be uh, the relationship can be even longer. Yeah, so this is the ancestor. Right. Of course, you have the ancestor, then you have the descendants. Yeah. So we say that B is a descendant of A and D, right? So this guy, B, is a descendant of A and also descendants of D. Yeah. So they have this relationship. Yeah, so the definition, A is an ancestor of B if either A is a parent of B, directly related, or A is a parent of some C, and C is an ancestor of B. So straight away, you can see that this is a recursive definition, right? Yeah, so that if A is directly the parents of C, A is the ancestor of C. Or if D is a parent of A, and then A is a parent of C. So D is also the ancestor of C. Yeah, so we have this definition. Right, three nodes. On the node on the tree, we have these three nodes, and some of them have some special name, right? So, for example, every node except the root node has a parent, has one parent. Okay, so we say that one node can have multiple children. Okay, but every node can have only one parent except the root. So this is a root. This guy no parent. Okay, but the rest of them will have a parent. Right? This one parents. This one have a parent. This one has a parent. Okay, so that is one important information that we need to know. And then, so therefore, this is a root node because this one has no parents, And then we have leaf nodes. Okay, a node with children, with no children is called a leaf node. So all these are leaf nodes, all the green leaf nodes. That means they have no children. So it is by itself without any node following it. Okay, so we have the root node, we have the leaf node. What about the other nodes? How do we call them? So in this case, we say that these are internal nodes. Okay, so we have the leaf node, and then including the root node, we are classifying them as the internal nodes. Okay, so has one or more children. All those internal nodes must have at least one child, or it could be more. And tree is recursive, as we said earlier. A tree is rooted on a vertex or on a node, and then after that you can have a subtree, and the subtree is again a tree. So therefore, it's actually a recursive definition. So this is the root of the whole tree, and this is the root of the subtree. This root have two children and have four vertices altogether. Yeah, so those are the things that we will have to know later on. Right, a node and all its descendants form a subtree. So any nodes inside here, you add in all the descendants, you will form a subtree. Right, so now we want to look at the level of the nodes in the tree. So this is important because subsequently we want to do some calculation. We want to get the height of the tree and so on. You have to use the level to be the first definition. Yeah. So number of nodes on the path from the root to the nodes, right? So therefore, this is root node. So the path that go from root node to root node is actually zero, right? There's no nodes on the path. But if you're talking about this path up to here, each one of them has one node to reach the root. Yeah. So therefore, A has level 1. Okay, B and C will have level 2 because you want to go from C to the root nodes, you have to go through two nodes. So the number of nodes on the path from root to the node is actually 2. Yeah, so that is a definition of the level. All right, so this level 1, level 0, this level 1, this level 2, and so on. Level 3. Okay, what is the height of a tree? Yeah, later on, you are going to see that when we talk about complexity of trees, data structures, the height is actually the one that is contributing to the complexity. So in this case, the definition of a height is the maximum level of the nodes in the tree is the height of the tree. So in this case, in the maximum level is actually 3, right? So remember just now, the example said that this is 0, 1, 2, 3. So the maximum level of this guy of this tree is actually equal to 3. Yeah, so that's why we have this. But take notes that this definition, we use this definition because subsequently I'm going to introduce to you the visual algo, which is actually a simulation. I will explain in a separate video. So in that visual algo, the definition is exactly what we see down here. But if you look at some book that you might be able to borrow from library, or you can go and buy some other textbook yourself, you might find that the definition is a little bit different, right? So for them, the height might be including this, the root. So if that's the case, then the height of that definition is equal to 4. But using our definition now, the height is actually equal to 3. So pay attention, remember this. If you are reading some other book, you cannot say, oh, they are wrong. it is not they are wrong. That is how they define the height. Okay, that's what we say down here. The other books might give you definition different from what you see down here. Okay, so this definition is because we want to be consistent with the definition given in Visual Algo. Size of the tree, they are very simple. We want to know how many vertices are on the tree, just like when we have size of the linked list, right? How many nodes on the linked list. So in this case, for example, uh, s- this tree has 10 vertices. So the size of the tree is equal to 10. But the subtree, in this case, the size of this subtree rooted at A is equal to 4 because there are 4 vertices. Right, so those are application, or sorry, those definition will be used in our discussion. So now we want to look at how tree can be used in solve in solving real life problem, right? So application of trees. So we say that a tree normally are used to represent data that are hierarchical in nature. Okay, so you have something on top, and then below it you have some other sub branches and so on. Okay, so the example, desktop or the file system. So you have this desktop, and then under the desktop you have many directory, right? The file inside there, and for each of the directory, sometimes we call it folder. You might have some other subdirectory. So this is a tree-like structures. And if you want to represent structures like this, a tree will be there and very natural, right? So you can never use linked list to represent this unless you are going to say that for each of these vertex, there are inside there there's an array or there's a linked list inside there, and for each nodes inside the linked list is actually another linked list, right? So that they make it very difficult to understand. So the tree will be easier to understand, but subsequently we are going to see that we are not going to consider general tree. We are going to consider only a one particular tree called binary tree, yeah, binary search tree. Okay, we'll come to that later on. Right, so you say a file system can be represented as a tree with the topmost directory as a root, right? In operating system term, this is also called the root directory. And then we can also use tree to represent aromatics expression, right? For example, given expression like this, we can actually use this tree to represent it, right? So you say that an aromatic expression can be represented by a tree as well, and there's no need to use bracket. So for example, this expression, we find that 2 plus is this. So everything on the left will be on the left subtree, and everything on the right of plus is on the right subtree. So similarly, looking at this subtree, there's a multiplication. So multiplication is actually the operation that you are going to perform on the left expression and the right expression. Right? So therefore, this is a left and this is a right. And inside here, because this is already at the left subtree of multiply, so this one is actually adding this A and B together to form an operand for the operator multiply. Okay, so now the question is, of course, given expression, how do you draw the tree? How do you represent it internally? Right, so yeah, you notice something. The leaf nodes are all variables, them all value, right? So just now we mentioned the definition of the leaf node, right? So these are all leaf nodes. Okay, so you notice that they are either value or variables. Okay, they are, yeah, right. Then the internal nodes, including the what they call root nodes, they are all the operator. Okay, so you can see that value are all stored inside the leaf node, and then the operation are all stored inside the internal nodes. All right, so just I was asking this question, how do you construct this? So by observation, we know that the root node must be the last operation that you want to perform. Okay, so in this what they call expression, we want to make sure that plus is actually the last operation that we want to perform. Then we will put plus as a root node, and then everything on the left will go to the left subtree. Everything on the right will go to the right subtree. But you can also say, I want to have the plus multiply to be the root node. Then this one will be a plus b, and this one will be a minus b plus 2. Right? So we can have different thing inside there. But once you have the expression tree, the bracket are implicit already. We do not need to worry about that anymore. Right. So of course, this is by observation. We can say, oh, if we want to do this one last, then this one will be here. But in the program that you are going to write, you can't say by observation because a computer cannot look at the expression and decide what is supposed to be. So we need to have some algorithm to normally convert infix expression. In this case, we say this is infix, okay, expression, because the operator come between the two. Right. So normally the like for example, computer calculator and so on, how do they evaluate the arithmetic expression? Normally, the first of all convert it to become postfix expression. We will look at it later on, or sometimes they call it reverse Porridge notation, NP reverse RPN. Yeah, so that the operator is actually behind. So, for example, in this case, we are going to have plus and then 2, and then we are going to have multiply, and then we are going to have minus, and then we are going to have B, A, and then we are going to have plus B, A. Okay, so this expression, infix expression, is going to be converted to this first. And then if this is actually the postfix expression, the computer will be able to see that I'm going to use this expression to be the last operation that I'm going to perform, right? And then on the left-hand side, on the right-hand side, I mean, on the left-hand side of this postfix expression, it must be the operand. Okay, if this is a value, straight away we know that it's supposed to go there. Although then I will know that this one is on the left subtree and so on. Okay, so we will look at this subsequently when we are discussing how to convert one expression to another one inside using a computer program. Right. So organization charts. For example, a big company, you have the boss of the company, and under it you have the uh, vice president of marketing, the vice president of manufacturing, and then under the marketing you have the director and so on. And below that you have the manager, and then you have the worker. So this is the organization chart, and you can actually use a three structures to actually represent this information, because this is basically hierarchical in nature. Right. So each employee, except the president, has only one immediate superior. So you do not need to report to two people unless you are holding the double appointment, right? So everyone else report to one person, and the president do not need to report to anyone else because he's the boss of the uh, of the company. Yeah. Right. Family tree. I don't know whether you recognize which family is this. The Simpson, right? The Simpson family. But then the question is, all these are actually seems to be father. Where are the mothers? For example, Abraham is a father, but who is a mother of Homer, and so on. So sometimes you might not be able to really represent the exact structures that you want to represent, in real life. Okay, so just now we say already, a tree in general is not very useful for us in this case. So for this course, we are more concentrating on binary tree. Okay, what is a binary tree? You say each node has at most two ordered children. So what you say is for each tree, for this binary tree, we have a vertex or a node, and each of these can have two uh, or no children. Okay, at most two children at most. Yeah. So I can have it like this. I can have two children here, and then each of them don't have any child. So this is actually a binary tree. Okay. So at most two ordered children. So what do you mean by ordered? Is it saying that they must be decreasing or increasing? The answer is no. This order means left and right subtree. Okay, so order from left to right. So in this case, we say that this vertex has a left subtree or left child, and then you have a right child. So this is what we call order. The order is left and right. Okay, so a binary tree says again, one node, every node has at most two ordered children. So this guy have two children. Okay, this guy has two children. Okay, but this guy has only one child. And all these leaf node have no children. Okay, so that is the meaning of a binary tree. Right, and again, we say this many times already. Tree is recursive, so therefore binary tree is also recursive. So for each of the subtree, it must be a binary tree also. So we don't want to have a the root node is having two children, but then the left child has more than two children. That is not a binary tree. So binary tree must be recursive, meaning that the definition applied to all the subtree. Yeah, they are all binary tree as well. Right, so the recursive, the same thing as I say, okay, meaning that the tree itself is recursive. All the subtree must be, sorry, the root node is a binary tree. All the subtree must also be binary tree. So that's the meaning of recursive here. Right, full binary tree. This is a definition. How do you define a full binary tree? So you say all nodes, all the nodes at level less than h. So remember, this is your h. Huh? So at level less than h means all this node must have two children. Then it is a full binary tree. Okay, where the height is actually the height of the tree. So meaning that for anything that is less than the height at this level, each one of them must have two children. Okay, and then this define by a full binary tree. Now, so the question is this definition equivalence the same as all nodes except the leaf nodes have two children? Is this definition the same as this definition? Okay, if you think about it before you can pause the video and think about it and then get your answer before you continue the video. Okay, the answer is no. Okay, so why? So the idea is if you say all nodes except the leaf node must have two children, you can have actually a leaf node down here with no children. So this is a leaf node, everything else is a leaf node, but it's not a complete tree, okay? Because um, some of the leaf nodes might not be in the at the on the same level, okay? So you can see that this is not a full tree, okay? So this is the only definition correctly describing a full tree. Yeah, all leaf node may not be at the same level. Yeah. Okay, so in natures, this is a real binary tree. Okay, someone took this picture and then give it to us for us to put inside this slide. So the main branch, you have two branches. For each of the two branches, they have two branches also. So this is actually a full binary tree. What about a complete binary tree? So full binary tree must be full, totally full. But a complete binary tree, the definition is this. Up to h minus 1 is a full tree, okay? Full down to level h minus 1. And then at level h, you fill the nodes from left to right. So if I want to add in one more nodes into this tree, I have to add it here so that this is complete. And if I have to add one more, if you try to add it over here, you will make this tree not complete. Okay, you must add this side first. So it's from left to right when you want adding the value into the complete tree. Okay, so pay attention to this because when we are talking about heap, we will be using complete binary tree. Yeah, so property, how many nodes in a full binary tree of height h? Meaning that if this is height equal to h, how many nodes do you have inside there? Right, the answer is the number of nodes is actually 2 to the power h plus 1 and then minus 1. So height is the height of this tree. So in this case, like for example, in this case, we know that height equal to 3, right? H is equal to 3. So 2 to the power h plus 1 means 2 to the power 4 and then minus 1. So 2 to the power 4 is 16, minus 1 give you 15. So you have 15 nodes out here. Okay, so the number of nodes is defined to be like that. Okay, you can use this to find the number of nodes inside a full tree. right? And then so therefore, if you think about it, the height of the tree of a full tree will be log n. So now the question is, how do you prove these two value? Right? How do you prove these two result? So the first one, if you really want to prove it, you need to use induction, okay? Induction. So therefore, like for example, h is equal to 0, then it is actually talking about one nodes, right? 2 to power 1 is equal to 2, minus 1 give you 1. When 2h is equal to 1, 1 plus 1 is equal to 2, 2 the power of 2 is equal to 4, minus 1 give you 3. So at level 1 or height 1, you have 3 nodes and so on. So how do you prove this? You first of all say that when h is equal to 0, it is correct. So when h is equal to 0, you have one node. Then you assume that h equal to k is correct. So we are saying that k plus 1 minus 1 is correct for a tree up to h equal to k. Yeah. Then after that, this is your induction. And then you want to prove that this induction is correct. How do you do it? Assume that this is correct. Then you want to go and prove that k plus 1 is correct. Okay, so assume that you have already have this. How do you find the rest below? Yeah. So the idea is we want to put k plus 1 inside here. If you put k plus 1 inside here, you are going to have k plus 2 minus 1. Okay, so we want to prove that this is actually the value. So how to do it? I will just give you some hints and then you can try to do it yourself. So how do you count the number of nodes in a full tree? We know that if you know the number of nodes on the subtree, which is, or this one is up to k plus 1, right? And this one is also k. So it's actually 1 plus nk, 2nk, because there are two of them. Okay, so nk is up to here, then k plus 1 is up to here. So if you substitute this guy inside here, okay, then you have 2 plus and then 2h, which is k, plus 1 minus 1. So what you want to do is prove that this guy is going to become equal to what we just now write. We want to prove that it's actually k plus 2 minus 1. Okay, so you want to go and expand this so that it eventually become this. And then you, by induction, you can prove that this is the correct one. Okay, and then what about the second one, log n? So this is important because subsequently we can use this as a complexity for anything that is involving tree, either full tree or complete tree. It is always log n. So how do you do it? We know that n is actually equal to 2 to the power of h plus 1 minus 1. So you just try to solve for h. So this will be n plus 1 is equal to 2h plus 1. So if you take log both sides, so log n plus 1, it will be equal to log, when we take log h plus 1 can go to the front, and then log 2. But if you are, for us, we say the log is actually base 2, right? Because it's binary. So log 2 is actually equal to 1. So you can see that log, so h, if you just move the 1 over, so h will be actually equal to log n plus 1 minus 1. Okay, so you can see that in big O notation, we say we can throw away the coefficient, or the constant. So this one is throw away. And over here, the inside here, you can also throw away. So therefore, it is actually equal to log n. Yeah, okay. Right, so this proved the two results. Yeah. And these are two important results that we have to keep. Right. So the other question is, if you are given a complete tree, what will be the maximum numbers of nodes or vertices, and what is the minimum numbers of vertices of height equal to h? Yeah. So it's actually equal. Yeah, easy because we know that up to h minus 1 is using this is a full tree using this, right? And then minimum means you have only one node over here. If you don't have this, then it's actually not a tree of this height. So you must have one node down here, and that gives you the minimum. Of course, the maximum will be a full tree. Yeah, so it will be very easy for you to just add using this to actually get the maximum. Right. So how do you implement a binary? Okay, so similar to linked list, we can do it in two different ways. One is by using reference base, meaning that you create a class where you have pointers inside there for you to get ready to create new nodes. Right. So linked list, you have a pointer to point to the nodes of the same or object of the same class. Okay. In this case, binary tree, you just have two pointer, one point to the left and one point to the right uh, for the same object of the same class. Yeah. So we can implement it that way. And in fact, we can also implement using array base. Okay, let's see how it is done. So similar to linked list, first of all, you must create the three nodes. Okay, linked list have a list node. Uh, Binary tree, you have to have the three nodes. So basically, similar thing. You put the object inside the nodes, and then you have two pointer, one pointing to the left, one pointing to the right. So every time you create a node, you are ready to create two more nodes because of the left and right pointer. And similarly, once you create this node, you will have two pointer available for you to use them to create new nodes. Of course, eventually you might say, okay, this guy have no children, so you stop here. Okay, so first you must have a list node uh, or three nodes in order to create a binary tree representation. Okay, and then of course you have to have the binary tree similar to linked list. You after you have having the list node, you have to create the linked list. So basically, this is the root. And then for a linked list, we call it the head. Now we call it the root. Yeah. So basically, it's just a pointer to getting ready for you to create a tree. Array base. Instead of saying using the left and right pointer, we use two indices, the left index and the right index to point to the left subtree and the right subtree. And the array representation looks something like this. Right, so inside here, the binary tree, this is the three nodes, this is actually binary tree. So you have the root, and then we need to indicate where are the free slots so that we can, when you do insertion, you can use this to insert a new value and so on. Yeah, and then the three nodes actually use an array to do it because we are using array-based implementation. And to represent this tree using array-based, you get something like this. Okay, so you can see that the root is actually at 2, index 2. So you can see this index 2. So A, the root node, is actually down here. Okay, and then on the left-hand side, the left subtree is 0, index 0. So the left subtree is actually L. The right subtree is 3. The index is equal to 3. So you go to 3, you find the right subtree. Okay, so this is S. And after that, similarly for S, if you want to find the left subtree, the left is the index is actually here. So therefore, you go to 1, you find the I there. Okay. And then, of course, the other side is empty. So we use -1 to say that there's no right subtree. Okay. And of course, for I, similarly, I just now we say is here, right? So there's no left subtree, but there's a right subtree at index 5. So you go to 5, you find the O. Okay. So that's how you represent. So the idea is this can be a record, a class of, no, so we said that this is actually a three nodes, right? So therefore, three nodes actually consists of three items. So you cannot say this is one array, this one array, this one array. No, this is actually a single array and each node has three value. Okay. Now, so when you are creating three representation using the array must be very big, right? You must have all the other places so that there must be some free space so that when you want to add in one more value, like for example, I want to add in here. Okay, let's say, how do I do it? So first of all, I have to use this free to identify the first free node. So this one is free, right? So I can put a K inside here. Then I go and do the updating. So K is actually on the left side of L. So of course you must know the when you want to insert, you can actually come down the path so you know the parents. So parent is over here. So you can update the left subtree of L to become 4, right? So you put the 4 inside here. So meaning that now L have a left subtree, okay? Then, and this become occupied already. 4 is actually for K, right? And K have no left and no right. So therefore it's minus minus. But now, where are the other free slot? So the problem is before that, you must have some other nodes down here that are free. So 4 is actually the first free slot. So how do you find the next free slot? You should use one of these. So either the left subtree or the right subtree, but for easy explanation, you just do this. So in this case, 4 is the first free slot. You might have a 6 down here to indicate that the next free slot is actually here. Okay, so once you have inserted this, you have to go and update the next free slot. So it's no longer 4 because you're using it already. So from here, you see the next free slot. So therefore, you are going to put this inside here, and this becomes 6. And you change this to -1 because this guy has no children. Okay, so that is how you actually using a array base to implement binary tree. Sometimes it is good, but most of the time I think this is troublesome. So normally we don't use array based implementation of a binary tree. Normally we use a reference base with left and right pointers. Okay, so how to handle the free space we have already said. So at the beginning, all of them are linked together as a linked list. Yeah, and every time you use one, you will point to the next one and make that to become the free space. Yeah. Right. So how do you represent a complete tree using array? So the idea is we say normally we use a reference base to represent a tree, but when the tree is complete, we know if we know that this tree is always complete because the algorithm requires it to be complete, then we can actually simply use an array to do it. And this is true when we are talking about heap, as we mentioned before. Right, so what you want to do is representing a complete tree using an array is actually very simple. So what do? You traverse the list or the tree in level order. Okay, level order. And then you put it into the index. So this is 0. And then you go on to the next one. You have 1. So you put this one into 1, index 1. You have 2, you put E into index 2. Okay, so you just traverse them in level order and then put the value into the array. Okay, and you will be able to represent this complete tree by using this array. Okay, now then how do you access the value after you have represented them into a complete tree? And it's very simple because you just need to use tree formula in order to find the left child, in order to find the right child, given the index of this particular value. And given the index of this particular value, you can find the parents. Yeah, so you just do all this. So given that a node is stored in index position I, what are the index position of the parents, left child, and the right child? Okay, so for example, let's say we look at this, index is equal to 1. I want to find the left child, is equal to 3. How do I compute this 3? And I want to find the right child, how do I compute this? How do I do that? So similarly, if I know that E is actually the nodes, I want to find the left child, the index will be 5, and the right child, the index will be 6. So what formula can we use in order to find the 5 and the 6 and so on? Okay, in fact, it turned out to be quite simple. It didn't show down here. Okay. So actually, given I, for example, 1, to find the left child is actually I times 2 plus 1. So 1 times 2 is equal to 2 plus 1 give you 3. The right child is actually I times 2 plus 2. So you get 4. Okay, if E is actually I is equal to 2, 2 times 2 plus 1 give you 5. 2 times 2 plus 2 give you 6. Okay, so that is the left child formula and this is the right child formula. For the parents, if I have this 6 or 5, I want to find the parents. I'm given the index 5, I want to find the parent index, which is 2. It's actually I divided by 2 and then plus 1, something like that. or I minus 1, oh sorry, I minus 1 divided by 2. Okay, so 5 minus 1 is equal to 4, divide by 2, integer division, I give you 2. 6 minus 1 divide by 2, 6 minus 1 is 5, divided by 2, integer division also give you 2. Okay, so that's actually the formula for finding the parents. Okay, so the height of the binary tree, as we said earlier, is the maximum level of the nodes in the tree is called the height. Yeah. So in this case, the maximum level is equal to 3. Remember, this is level 0, 1, 2, 3. So therefore, the height of this is equal to 3. Again, warn you that different book might give you different definition. So height equal to 3. And the height of a binary tree, how do you find it? If you have to write a program to do it. So the height of the tree is actually equal to empty at 0 if it is empty. Otherwise, you will add 1 to the maximum of the maximum height of the left subtree and the right subtree. Yeah, so you find the maximum. And you add 1 to it will give you the height of the whole tree. Yeah. T left and T right represent the left and the right subtree of node T as respectively. Okay, so it's actually quite simple. So if I have a root node pointed to by T, okay, there's a left subtree, there's another, and then we have this, let's say. So you can see that this tree on the left, the height is actually equal to 1. This tree on over here, the height is equal to 2. Right? So therefore, you use the maximum of the 2 tree, which is equal to 2 and add 1. So therefore, the height of this guy is actually equal to 3. Okay, which is correct 0, 1, 2, 3. Yeah. And again, this is recursive. Yeah, you can see that the height of the T is equal to the maximum height of the subtree on the left and the height of the subtree on the right. Take the maximum of the two, and then so therefore to find the height of the left subtree, you just call the same method again. And so therefore this is actually recursive. Right, size of the binary tree, as we say already, is just counting the number of nodes inside there. So the size of the left subtree, this subtree is equal to 4. Over here is equal to 4, and you add 1 to it, you get 9. So therefore, in this case, it's not going to become maximum of the left or right subtree, but you just count all of them. Yeah, so you have something like this. If t is equal to empty, return 0. That means it's empty tree, so size is equal to 0. Otherwise, it's S1 plus the sign of the left subtree plus sign of the right subtree. Very simple to understand. Okay, so given the binary tree, if you want to find the value inside there, you want to, like, for example, inserting something, you have to traverse the tree to the bottom in order to insert there, and so on. So binary traversal, how do you do searching? How do you traverse the value in order to make some decision, in order to do some calculation? How do you do that? Okay, so we say that there are actually 4 possible order of traversal. So we have the post order, we have the pre-order, we have the in order, and we have the level order. So you have seen level order already, right? So you just traverse level by level, and then starting look at the index, and then just look at the value inside there. So this is what we call level traversal. You have seen it already. So what is post order traversal? Right, so most of the time the words is actually giving us a hint. Okay, post means after, right? After. So what do you mean by after? So we have this tree down here. Okay, so this is a root node. Let's say T. Post means after I have finished traversing the left subtree and finish traversing the right subtree before I visit the root nodes. And this is what we call post. After you traverse the left, after you traverse the right, then you go and visit the root nodes. This is post. Pre, the opposite. You visit the root node first before you traverse the left subtree recursively, and then you traverse the right subtree recursively. That will give you the pre-order traversal. Right? In-order traversal in between. So you do the left subtree first, and then you visit the root nodes before you go and visit the right subtree. Okay, so these are the 4 possible way of traversing the binary tree. And then you notice something. if you think about it, you can say left, R, right, and then N is a node. This one is actually N, L, R. Okay, the node, the root node comes first. This one is L, N, R. Right, so the root node is actually in the middle. So that's why it's called in order traversal. Now, so this is always left to right because this order, right? Our binary tree is order from left to right. What happens if I want to get reverse order? Then you just traverse it from right to left, right? If I do N, R, L, I will get a reverse order of this guy. Okay, so that is possible. For certain application, you might want to have the thing reverse before you use them. All right, look at some example. So post-order traversal traverse the root after traversing the left and right subtree. So that is the definition. So how do you do it? Post-order traversal of the tree. If T is not empty, you just go back, okay, return. Although if it is not empty, what you want to do is you recursively traverse the left subtree in post order, exactly the same. And then you post order the right subtree, and finally you go and print the item inside the root. Okay, so you can print, you can actually do some processing and so on. Okay, basically this is actually a post order traversal recursively. So now, most of the time we say if you have a recursive algorithm, you can always convert it to become an iterative one. So how do you do this? Just give you some hints. The idea is you have a T down here. So if you go down to the left subtree to do this, and then you want to go down to the right subtree to do this, how do you, after doing the left subtree, you can able to come up here, and after doing the right subtree, you can come up here to process a root node. So you can see that you must store the index or the reference somewhere, right? So before you go down, you have to store this index, this reference somewhere, right? And then remember they are recursively true also. So how do you store this guy? It must be on a stack, right? You use a stack to actually store this guy before you go down. And at the same time, before you go down, you store. So let's say this is actually pointer A, pointer B. So when you come down to B, before you go down, you have to stack the A first. So that when you finish this, you pop this up, you will be able to go back to here. And in order to come down here, of course, again, you have to put A inside the stack again, so that after you finish the right subtree, you can go back here. Okay, so in this case, because of post order, you have to go down, come back, go down, come back. So you have to actually store A 2 times, right? So you have to indicate to yourself whether this is the first time that I store A inside here, or this is the second time I store A inside here. Because if it's the first time, I need to go down to the right subtree. I have to store it one more time, okay? But if it's the second time already, when I pop it, I know that I have already finished left and right. So therefore, I can actually visit the root nodes. Okay, so using a stack to help you to do post-order traversal. But it is not straightforward. Remember, you have to keep it twice inside the stack, not just one time. Okay, so this is a recursive solution, and then ask you whether you can give a iterative solution. So I have already given you the hints. Use a stack to do it. Right, so example. Right, so want to traverse this in post order. So we know that you have to first of all traverse this in post order, and then to traverse this in post order, I have to traverse this in post order. So there's nothing there, so I output 4. Then I go and traverse this in post order. So I traverse this first, so I have 8, and then I have this 9. So now I finish the left subtree of 5, finish the right subtree of 5, I traverse 5, I visit 5. Right, so now I finish the left subtree of 2, I finish the right subtree of 2, so I can go to 2 and output the 2. Right, then now I have to go to the right hand subtree and then do this one. So I go down, 6 has a, what they call, right subtree, so I have to traverse the 0 first, and then I go to 6, and then I have to go to the 7 before I go to 3. So now I finish the left subtree, I finish the right subtree, I traverse the root node. So I should get this. Okay, let's see whether we are correct. Yeah, 489-520-6731. So that's what we call post order traversal. try it out yourself. If you are not clear, go through the video again. Right. So pre-order, as we say, is visit the root node first. Otherwise, they are exactly the same. Okay. And then this will be the pseudocode. Pre-order, if the tree is empty, you just return. Otherwise, you print it first. Print the value inside or process the value inside the root nodes. Before you go to the left side, you go to the right side recursively. Okay. And you are done. So I don't think I need to explain using the picture. You can visualize it, but we can use an example. So traverse this tree in pre-order. So we know that. So first of all, you have to do one first, and then after that you do two, you do four, you do five, you do eight, you do nine, 3, 6, 0, 7. Yeah, so that would be the answer. 1, 2, 4, 5, 8, 9, 3, 6, 0, 7. Yeah, very simple. So what about doing this in iterative? So we know that after you traverse this, when you go down to the left-hand side, you need to come back here to go to the right. So again, you still need to keep this inside there, inside the stack. But in this case, you only uh, go down and come up once, right? Because once you are over here, you have already processed this. You do not need to come back here anymore. So therefore, you use the stack, but only put the value inside there once only. In order, very simple, in between the left side and the right side. Okay. So again, the pseudocode will look something like this. I do the left subtree, I visit the root nodes, and then I go and do the right subtree in recursive call. Yeah. Okay. So again, you can do this. If during exam, if I give you this uh, example, it's actually quite simple. I can just pull this one down, put it here, pull this one down, put it here, pull this one down, put it here. 5, 9. Okay. 1, you have to make sure that you don't cross anything. And then you have the 6, you have the 0, you have the 3, and you have the 7. So if you are just doing it by observation, it's actually very simple. You just pull down the thing and don't cut any branches or any edges, and you get the in order sequence. So let's see whether we got it correct. Yeah, 4, 2, 8, 5, 9, 1, 6, 0, 3, 7. Yeah, so they're exactly correct. Okay, so later on, you are going to see that if this is a binary search tree, after we give you the what you call definition, given a binary search tree, if you traverse it in order, you are going to get a sorted sequence. Okay, that will be coming up soon. Okay, level traversal we have already seen, but we can actually look at the program and see how it is done. Okay, so it says traverse the tree level by level from left to right. Right, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. Yeah, that would be the level traversal order. So this is pseudocode, and remember this. If you need to do something called DFS, so previously the level traversal, no, sorry, the pre and post and then in order, they are all actually doing it using a stack. Okay, but when you are doing in order, level order, you have to use the queue. Okay, you have to use a queue. We will explain why. Right, so the idea is if T is empty, you just return. Nothing can be found, right? Otherwise, you want to create a new queue. Okay, you create a new queue, and then you push or you enqueue the root. Okay, you enqueue the T. Yeah, and then after that, you go inside a while loop. Okay, and do until the queue become empty. Right, so while queue is not empty, you will do this, dequeue the T, and then make it to become current. And because this is level order, you can print it straight away. And then once you print it, you want to look at the two children because this is binary, right? So the left child and the right child. And then remember we say the order is important. That's exactly the case. Okay, left child and right child. You put these two children into the queue. Okay, if current left is not empty, you enqueue. And then if current right is not empty, you enqueue the right. Okay, and then after that, you go back to the while loop. So why do you use a queue instead of a stack? Because you need to do first in, first out. So you can see that this one has two children. I need to make sure that two go out first before three. And that is a natural way to achieve by using a queue. Right, so level traversal, you want to use a queue. So the queue, the current point, and then the print, what is output. So first of all, you go to this level, which is one. You enqueue one inside there. That is the beginning, right? Before the while loop. And then you go to the while loop, the queue become empty. The current is actually equal to one, and then we print one. So this is a dequeue operation when inside the for loop, inside the loop. Okay. So now I have already used up the current. I need to enqueue the two and three. Okay, so I enqueue 2 and 3, the queue will have 2 and 3 inside there. And then go back to the while loop, the 2 will be taken out. So 3 remain inside the queue. And then 2 is the current one, we print out 2. Okay, and then what do? You have to go and dequeue 4 and 5, right? So dequeue 4 and 5. So previously 3 is the orange, is the the lone number inside there. So now enqueue 4 and 5. Okay, then you go up to the loop again, and then you take out 3. So once you take out 3, then the queue become 4 and 5. And then what you do, the processing, you are going to move 6 and 7 inside the queue. Okay. And then you can see that this is exactly what we want. Okay. Level travel, level by level, and then the value is from left to right. So you just continue with this animation. Right. Eventually you finish and then you have an empty queue. So therefore the algorithm stop. Okay. Right, so now the question is, what is the maximum number of nodes inside the queue? Okay, so queue, if you think about why we ask this question, the idea is that if you want to use array to represent this queue, then you have to be careful, okay, because we do not know how many are inside here. But actually, if you make an observation, the number of nodes is actually here. Okay, but of course, if there are small things down here, if it is a full tree, then the maximum queue is actually this whole thing. Yeah. So this is just a estimate. With a binary tree like this, the maximum is equal to six. No, four. You can see that four here, four here, four here. Yeah. So that is the maximum that you have. But we cannot predict that this is going to be uh, the maximum. So therefore, normally it is actually better if you use what they call a linked list to represent the queue, so that there's no limit on the number of elements that you can have inside there. If you use the index to represent array to represent the queue, you can, but you have to reserve a very big array in order that you don't run out of space. Yeah, and that will be wasting memory space. Right, and then what is the mean implementation problem of level order traversal? So the idea is if you use array, you are going to get a problem with the queue size, the size of the queue. Yeah. Okay, so expression tree, how do you represent them? How do you evaluate them? Okay, given some expression tree. Right, so evaluating expression tree is go this way. So you can see that every internal node is an operator, and for each operator, for this one we are just dealing with a binary tree, right? So each one of them will have two operand. Yeah, so the two operand for this operation plus or addition is actually A and B. For this minus operation subtract is also A and B, yeah, and so on. So we can represent this without any needs of bracket, okay, because it's actually implicit inside that. Okay, so these are operand on the leaf nodes. Internal nodes are operator. So this one you can observe and you can see easily. Yeah. Okay, so if you traverse the expression tree, you're supposed to get the result. If you do it uh, in order, right? If you do it in order, meaning that you traverse the left side first, you traverse the right side, you get these two values, you go and apply the value in the root nodes. Yeah, so post order traversal will give you this. As I said, by looking at it and say we can do it in order so that we can get the answer, it's not so simple because internally the computer don't look at the expression or don't look at the expression. They actually create the what they call post order traversal, and then after that get the postfix expression. All right, so this is what we call the postfix expression of the expression tree. You get this. And then once you have this, it will be very easy for you to do the evaluation. Okay. All right, so what are the infix and prefix expression of the tree? Prefix means the plus is in front, followed by multiply, followed by plus, and so on, right? So this is prefix. And then if it is infix, you are going to have this one on the left-hand side and this one on the right-hand side of the plus. Right. So what is the arithmetic expression of this expression tree? You should get this answer. That is a post order. Okay, so how do you evaluate the expression tree? So if the D is empty, you return. Otherwise, you go and evaluate the left subtree. So if it is a leaf by itself, it is actually a value, just return the value. Otherwise, if it is plus, you go and evaluate the left subtree and then evaluate the right subtree and then apply this operation plus to it, and then you can return one value for adding two subtree. Right. Otherwise, if it's multiply, you just multiply the value. Right. If it is divide and minus, you have to be careful because plus and addition is actually permutation. What is the word? Not permutation. Cannot remember. Yeah. Okay. So anyway, what we are trying to say is A plus B is actually equal to B plus A. Similarly, multiplication are the same. So we don't care about the order, right? But when you are doing divide and minus, A minus B and B minus A are different values. So you have to be careful about this. Right, so how to handle other arithmetic expression, like for example, divide minus, and then you have the unary minus. Unary minus means there's something missing in the expression tree because it didn't take two, what they call operands. Right, so you say, do we still need to consider priority? And the answer is no, okay? Because it's actually inherent inside the tree itself. Right. So another important tree that we want to study beside binary tree, because sometimes it is not really useful if you have just had a binary tree. Okay, of course you can represent the information. But the more important data structures that we are going to study is called binary search tree. Yeah, this is very important. You can actually solve many different questions, different problems. So you should get yourself familiar, very familiar with this. Okay, so the definition is this. BSD organize data in the binary tree such that all keys smaller than the root nodes are stored on the left subtree. What it means is this is a root node, let's say for example 10. Any value that is smaller than 10 will be on the left subtree. So that is what it means by all keys smaller than the root are stored on the left subtree. And so similarly, all value that are greater than the root will be stored in the right subtree. Yeah. So this is actually quite simple in the sense, meaning that everything, the root nodes will be greater than everything on the left, and the root node is actually smaller than everything on the right, at most equal. Okay, so can we have nodes with the same key inside the BSD? It depends. So sometimes you want to allow because all these key might represent different things. Yeah. So therefore, you have to indicate if this is the same, what kind of convention you are going to use to store them. Because if you don't follow some convention, you are going to get lost because their key are different. Okay. Right. So you recall a table is look like this. So basically, the table have three functions that we want to operate: insertion, deletion, and searching. Okay. So like for example, you have phone books, right? So their phone book is actually created such that the numbers or the name of the person is actually in alphabetical order. Street directory, dictionary, class schedule, they are all the same. Yeah. So in this case, how do you do or represent this in binary search tree, and then what can you get from this binary search tree? So ADT table operation, if you think about it, we know that there are three operations: insert, delete, and search. Yeah? Right, so searching the data using the key, you want to insert the new data using the key, you want to delete the key because it's no longer useful. Yeah. And then if you think about it, the running time of the six of the operation, if you are doing unsorted array, to search, you have to, the worst case is ON, right? And then if to insert, you just insert it at the back. To delete, you have to search for it again, so another ON. Sorted array searching can be done in log n time. Okay, insertion is ON because after you find the insertion point, you need to open the gap, and opening the gap is ON. Similarly, delete the value inside the array, you have to uh, close the gap. So that is an ON also. Sorted linked list, if you want to do searching, because it's sorted, but it is not having any pointer to guide you from one nodes to another. So you might be searching from beginning to end, which is ON. To insert, you have to search for it first before you insert. But this come if you use two pointer, the insertion operation itself is only O1 because you just reset two pointer. But searching sort you cannot do binary search because on a linked list you cannot go to the middle. To go to the middle, you have to start from the beginning and then following the link to go to the middle, and which is already ON. Okay, deletion, you have to search for it first before you delete. Yeah, so this is a table giving the running time of the operation. Okay, so you answer this question, unsorted array least implementation better than sorted array. So if this is unsorted, do you think it is actually better than this? You can see that insert is actually much better. Okay, so if you think about it, if you just consider sorted array, in fact, searching is actually very fast. Okay, but if you're not going to do searching all the time, you are just doing insertion, then actually maybe you want to consider the second option. Yeah. Okay, so you can see that unsorted array list implementation, unsorted array, this is actually much better than sorted array. Can we use a tag or a queue to implement table ADT, and why? Okay, so the table ADT is actually the three operation, right? Insert, delete, and search, right? And currently we are talking about binary search tree. So the question is, can we make the um, ADT become more efficient and so on? Can we use a stack to help us to improve the efficiency? Can we use a queue to help us to improve the efficiency? So again, I'm going to leave this to you to think about it, and then look at the resources inside the website Cosmology after you have think through this. Right, so binary search tree, to do insertion, to do deletion, to do search can be done in OH time. Right, so H is actually the height of the BSD. Now, this is not a guaranteed value. Okay, so it depends on the how you insert the value one by one. Because if you are unlucky, every time you insert, remember to insert into a BSD, uh, if the value is smaller than the root node, you have to go to the left and then check the root node of the subtree. Similarly, if it is smaller, you go to the left. So eventually, you cannot go down any further. You might want to insert the value inside here. So it depends on the height of the tree. So this height is actually uh, random depending on the uh, insertion that you have done. Okay, so height is actually respective to n, the number of nodes. Yeah. The performance of update operation of BSD better than unsorted and sorted array? Okay, it depends whether you balance it or not. So we are going to discuss this in the next video called ABL3. Yeah, ABL3. I must be tired. Okay, what are the worst case? The worst case is every time you insert, what happen? you always go to either go to the left all the way until the last, or you always go to the right. So then actually this insertion resulted in a linked list because it's always go to one side. That is the worst case. So the height is basically equal to the size of the data. Right, so the BSD property, you can use this picture to represent it or to show. So this X is a value. Everything on the left side is less than X. Everything on the right side is greater than X. That's it. That is a property of a BSD. Right, organize the data in such a way that all keys smaller than the roots are stored on the left subtree. All key that is larger than the root nodes are stored in the right subtree. Right, so for example, is this binary search tree? The answer is no, because one is not greater than everything on the left, and one, okay, is smaller than everything on the left, on the right, but is already violating the uh, definition of a binary search tree. Not, so this is not a BSD, yeah, because left side has greater value than the root nodes. What about this? So you can check phi is a root node. Everything on the left is smaller than phi. Everything on the right is greater than phi. So we say that, of course, you have to recursively check. So for this guy, 0 is over here. Everything greater is over here. So for 3, 2 is smaller. So therefore on the right, on the left, 4 is greater. So therefore it's on the right. So and so on. Okay. See. So why is this not? Okay, so this side is okay, but what about this side? 8 greater than 7 and 6. 8, okay, so this is a problem, right? So 7 is actually greater than 6. So 6 should be on the left side of 7 rather than on the right side of 7. So this is not a BSD, okay? Right, this is a BSD. Everything on the left smaller, everything on the right bigger. For over here, 8, 6 and 7 are smaller, and 7 is bigger than 6 and so on. So this is a BSD. Right, so as we say earlier, if I traverse this in order, because this is a BSD, right, we know that this guy, if you put it down, is going to become the middle of the uh, element, right? And everything on the left-hand side is smaller. So we have all these elements are smaller and recursively true. So 5 is at the correct sorted position. And over here, 6, 7, 8, 9 will be on the right-hand side. Okay, so you can do the traversal yourself. Right, so if you traverse a BSD in order, you are going to get an increasing order sequence. Right, operation on BSD, meaning that insert, delete, and the search. So if you want to find the minimum element in a BSD, we know that if you go here, if there's a left subtree smaller, some value smaller than the root will be on the left subtree. So you have to go down, right? So again, you go to the root node of the subtree, and if this guy no minus value, nothing behind or in front of it, then this guy must be the minimum value. Right, so you're just going to go left all the way until you cannot go any further. That should find you the minimum elements. Right, so if X has a left subtree, then the minimum element should be in the left subtree. Otherwise, the minimum element is X. So that's how you can write the algorithm to solve this problem. Okay, finding minimum. So you can see that if phi is a root node, I come inside here, which is T. So there's a left subtree, so I go to the left. There's a left subtree, I go to the left. And then this guy have no left subtree. So therefore, 1 is the minimum elements. Okay. For the same argument, 9 will be the maximum. So we know that 9, you have to go right. So 9 is greater than 5, so you go right. 8 is greater than 9 is greater than 8, so you go right. And then 9 is equal to 9, so therefore you found the maximum value. Right, so while T is not empty, you go T left. Just do that, okay, until you cannot go T left any longer. That will be the minimum value. And similarly, if you want to find the maximum value, you just t right all the time until t right is empty. Then you return the value inside there. Okay, so we have already mentioned this. And how to find the top k or bottom k elements. So that, for example, the top three. So we know that you the top elements must be on the right hand side, right? So if you say top one, it will be the maximum, and then top two will be the maximum. The root before this maximum nodes. Yeah, so you can actually do a recursive algorithm to find top k and bottom k. Searching in X, you want to find a value, right? In this case, we say that this is an iterative solution. So we know that iterative means you use a stack. Yeah. So while the T is not empty, if T item is equal to X, then you return the T. You point out which nodes or which vertex actually contain the T. Otherwise, if the T item is greater than X, because now we are searching for X inside T, right? So if this item is greater than this, that means we have to go uh, so X is actually the value that we are searching for, and the T item is greater, so therefore X must be on the left-hand side of the T item. Okay, that's why you go to the left. Otherwise, you go to the right. Otherwise, you return now. Yeah. So searching, how do you do it? If T is empty, return now. You cannot find. If they are the same, you return the pointer pointing to the T nodes. If X is less than T dot item, X is too small. So what you want to do is you want to look at the left-hand side of this T, right? Because and then you search for it. So this T is actually a dynamic place value. Okay, uh, you look at the item and then you just check whether the X that you are searching for is actually smaller than this item or greater than this item, and then you search using the correct path. Okay, so you have this, and then you are done. So which solution is faster, iterative or recursive? Again, you want to think about this before you come back and then look at the answer. So the idea is iterative is very simple. You just use a queue, right? No, you use a stack because you need to go down and go up. So you just use a stack and then you will be able to get the answer. But the idea is every time you use a stack, you have to store the what you call um, reference and so on, so that you can go back up to do it. Right. So if you want to use a for loop, you will be actually faster. Iterative will be faster actually. Insertion, I want to insert 6. So remember, this is a BST. You want to do insertion, you have to follow BST way of inserting the value, right? So when this is 6, you come here, what do? Compare 6 with 5. 6 is bigger, so you come down this path. So you compare 6 with 8. 8 is more bigger, so you come over here. Then you get 7. 7 is still bigger than 6, so we know that we are supposed to insert 6 down here. Okay, so that is how you do insertion, but how do you write the function to do it? Okay, after insertion 6, after inserting 6, it become like that. Okay, so insert x to t. If t is empty, you just insert the x as a value and create this tree with only one node. Otherwise, if x is less than t item, so x coming in, t item is 5. Like for example, I want to do 2. So you will go to the left side. Okay, insert this new value to the left side of what we are having. Eventually, you're going to come to 1 down here. Then you are going to insert the new value on the left side of 1. Otherwise, the other way around. Okay, so this is quite symmetric. Otherwise, there's an error uh, because x should actually equal to the t item. And then after that, you return the t, which is a node pointing to the solution. Right, so you say that this method assume that we don't allow duplicate key inside there. That's why we have the smaller than and greater than. We didn't have the equal signs. Okay, so in this case, this pseudocode does not consider everything possible. It just give you the duplicate key values in the BSD. if we allow BSD, then how do we modify this method? So that means you must take care of the equal sign here, right? And then you do something here. Okay, so the idea is like for example, let's say I have a 3 is actually equal to the T. And then I want to find a place to insert maybe uh, 2.6 or something like that. Okay, so smaller than this, you come over here. Greater than this, you go over here. And greater than this, you go over there. So maybe you get 2.6 and put it inside here. But then you can see that there's a problem because you are coming down from this side. So the height of this guy is actually 4. Right? You count this as 1, 2, 3, 4. So 2.4 is actually the uh, fee for your eyes uh, checkup uh, with the medicine. Right, where to insert it before or after the duplicate key. So if you want to allow duplicate key, you must come up with your own convention, right? Always go to the right hand side if they are equal. And then where to insert it, you just follow the insertion, and every time you go to the using the same convention, you insert the value inside the tree. How about deletion? So insertion and searching is very simple. You just follow the BSD property. Greater you go to the right, smaller you go to the left. But now when you delete, you have to be careful, okay? Because you can delete a node that have 2 children. And then which one do you put on top in order to preserve the BSD property? So let's see. Okay, so if there's no children, you just return the item itself. Uh, You just return empty tree. There's no because no children, and I want to delete this particular node. Otherwise, you have to say not found. Okay, because you want to look for this and remove it from your database, but you cannot find it. You have to say not found. Right. So if you have this node, I want to delete 4, so therefore I'm just going to return the empty tree. Case 2, you delete a node or vertex with one child. So in this case, first consider 2A is actually the left child, right? Something like this. So if that's the case, if I want to delete this node, just simply return this pointer. So that's you can attach this to some other uh, modules or some other materials. Okay, otherwise, if X is less than the T item, then you go to the T left and try to delete the X from the T left. So this is again recursive, right? Because X is smaller than the T item, smaller than this guy, and we know that this is T, yeah? We know that if it's smaller, it must be inside here unless it's not far, right? So therefore, you go and delete uh, T dot left with the same value X, okay? And then you just continue until it is done. Now, one of the things that you might be wondering, what is the meaning of T dot left is equal to delete T dot left. So the idea is this, when you are going down to here, T is down here. And because I'm not deleting this, I want to delete something below. I need to pass this value into the delete, okay? And in a sense, I'm just cutting off this for me to send this whole bunch to the left subtree, to the delete operation. Now, so the idea is you can consider this t dot left. Why are we doing this assignment, right? So we send this t dot left to the delete function. The function can delete the root nodes and then return a value. So it's actually the reference coming back after you do the deletion. So I need to put it back to T left because this guy come from T left. Whatever is left after the deletion, you should attach it to the T left. Okay? Otherwise, it's not found. Then you return T, yeah. So delete 5. If you delete 5 down here, you will just return 3 and then attach to whatever parents coming down. Okay, case 2 is similar, except that it's on the other corner, the other side. I have only one child, okay? The diagram look like this. So therefore, if you remove this, then you will have only the left child, the right child. Similarly, if it's not correct, you can actually call this right delete to actually give you the answer. Okay, again, delete 5, you just return the pointer 8 to the previous uh, discussion. Okay, so case 3 is when you delete a nodes that have two children. For example, I want to delete 5. So there are two children, 3 and 8. So the question is who will become the root nodes after 5 is deleted, right? So if you say I put the 8 inside on top, then you are going to have problem because 7 and 6 are actually smaller than 8. They should go the other side. If I say I use a 4 to replace, then it's actually okay. Yeah. And in fact, this is okay, not just okay, this is the way to do it. So you can either use the in order predecessor, which means if you draw it in order, this is actually 5. The preprocessor is actually equal to 4. That means directly in front of the value that you are deleting if you traverse it in order. Right. Otherwise, you can also use the minimum value on the right hand side. Okay. This 6. So it's either I take out this, I put the 4 inside there, or I take out this and I put the 6 inside there. Right. So 6 inside here, go to the right and then go to the left and so on. So you can actually reserve some of the complexity. Yeah. Drop this. You replace it with the smallest value on the right subtree. Okay, so you can see straight away that everything on the right is greater than 6. Everything on the left is smaller than 6. And that's why we have to do this. Okay, another way is moving the largest value, 4, to 6. Yeah, that's another possible uh, uh, improvement. So you can actually say I find the in-order predecessor or I find the in-order successor. And either one of them can be used to replace the value that you are deleting. Okay, if you delete a node that have two children, so what you do, you check if it is equal to the item, then you just find the minimum of the two, the T right and the T left. So this is actually finding the minimum item on the right is actually finding the in order successor. And then you replace this T item that is found, and then you actually uh, because it's on the minimum on the T right. So you get this item, you are going to put this item on the value that you have deleted, replacing the value that you have deleted. Right. Then after that, you go and remove the value on the right hand side. Yeah. Otherwise, you know that it's the value is smaller than T, so you go to the left hand side in order to delete that value from there. Right. So what is the running time of BSD? We said that 5 minutes is equal to OH, depending on the height. So like for example, you go left, 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 and then it's actually a linked list. Then OH is actually equal to the number of nodes, right? But you know that you can just go down the left-hand side to find the minimum, uh, which is actually equal to OH. Searching is OH because the worst case is you search until the bottom of the tree. You cannot get more than OH. So insertion is OH. You go all the way to the bottom and insert the value there. And then deletion is OH because you have to find it first and then you have to replace. When you want to replace, you go down all the way to the minimum or to the maximum of the two subtree. So all these are OH. Right. So now whether these are efficient, whether it's better than the linear list, we will check. But H is not always log n, okay? Because as I say, you have a skewed uh, linked list, then it's not log n anymore. It's actually equal to it's equal to n. Okay, so in this case, when it is balanced, it's good. So the highest level is actually equal to 2. So you can go down to 2 steps in order to find the value that you want. Okay, so this balance. But what happens if it is not balanced? You are going to get this problem. No longer log n, but rather you get on, right? So when you insert node in increasing or decreasing order, you get a skewed tree, and the height is actually on. Okay, so that end the discussion of this chapter on tree. I hope you can understand. If not, view it a few more times, and you should be fine.